Hi, Assalamualaikum. My name is Nafisa, and right now I will be presenting about the electricity and magnetism physics 568. This presentation was prepared for Dr. Faris. My main focus will be on a topic that underpins the entire concept of electric and magnetic fields, which is vector analysis. Before we dive deeper, let us take a look at the overall roadmap for the vector topic. We have vector analysis, coordinate system, and also Maxwell equations. What exactly is a vector? As we know, vector analysis involves quantities that process both magnitude and directions, which differentiates them from scalar quantities that only have magnitude. Unit vector, denoted as small a, it is defined as a vector A divided by its own magnitude. What is magnitude? Magnitude is to find the length or value of a vector. We use the Pythagorean theorem. For a two-dimensional space, the magnitude is given by a equal to square root a squared x plus a squared y. For a three-dimensional space, we simply include the z component, making it a equal to square root a squared x plus a squared y plus a squared z. Vectors in terms of component. Any complete vector can be written by multiplying its magnitude along each axis by its respective unit vector. Now, we move on to geometric vector operations, specifically vector addition and vector subtraction. There are two primary geometric methods to add two vectors. Let's say vector u and vector v. First method, head to tail. We place the tail of the second vector at the head of the first vector. The resultant vector, u plus v, is drawn directly from the tail of the first vector to the head of the second vector. Number 2, parallelogram method. We join the tails of both vectors u and v at a common origin, then construct a parallelogram. The diagonal starting from the origin represents the resultant vector u plus v. For vector subtraction, the operation u minus v is mathematically handled as adding vector u to the negative of a vector v, which is u plus minus v. Geometrically, the direction of vector v is reversed by 180 degrees before applying the standard addition method. Moving on, let us look at the concept of the position vector, which is also referred to as the radius vector. The position vector of a point P is defined as its distance and direction from the origin 0, 0, 0. Generally, the formula for a position vector is written as Rp equal to x ax plus y ay plus z az. Let's look at the graphical illustration provided. If we have a point P with specific coordinates 3, 4, 5, it means this point is located at x equal to 3, y equal to 4, and z equal to 5. Therefore, its position vector, P, can be precisely expressed as P equals to 3ax plus 4ay plus 5az. This concept is crucial in electromagnetics because we have constantly need to specify the position of electric charge in a 3D space before we calculating the resulting fields. The final part of basis vector analysis involves multiplying two vectors. There are two distinct types of vector products. First, dot product, scalar product. The dot product between vector A and B results in a scalar value. Its formula is A dot B equals to AB cos theta AB, or by assuming the product of their respective components. AX BX plus AY BY plus AZ BZ. We use the dot product when we want to find the projection of one vector onto another, or when calculating physical quantities like work done and electric flux. Number 2, we have cross product, vector product. On the other hand, the cross product yields a new vector that is perpendicular to both original vectors. The formula is given as A times B equals to AB sine theta AB. To solve this algebraically using components, we evaluate A 3 times 3, determining matrix as displayed on the slide. Expanding this matrix gives us the final vector components for the AX, AY, and AZ axes. Now, let's move into coordinate systems, which are essential tools for solving Maxwell equations. depending on the structural symmetry of our problem. We use three primary systems: Cartesian, cylindrical, and spherical. Here is how a vector field A is expressed in each framework. In Cartesian, it is broken into linear components AX, AY, and AZ. In cylindrical, we use radius, angle, and height. We have A rho, A phi, and A Z. In spherical, it is defined purely by special shell's attributes. We have AR, A theta, and A phi. To switch between these geometries, we use point transformation formulas. For example, to convert Cartesian to cylindrical, we use rho equal to square root x squared plus y squared, and phi equals to 10 to the power of -1 multiplied by y over x. And for spherical to Cartesian, we use standard trigonometric breakdowns like x equal to r sin theta cos phi. Besides coordinates, we must also transform the actual vector components using transformation matrices. As shown on the slide, converting fields between cylindrical and spherical forms requires multiplying the column vector by a matrix containing sin theta and cos theta factors. This master table consolidates all possible conversions between unit vectors and field elements across all three systems. It serves as a quick reference sheet whenever we handle varying boundary conditions in electromagnetics. Finally, to perform vector calculus in Maxwell's equations, we need the correct differential elements. Line elements dl, used for path integrals, surface element ds, is crucial for finding flux in Gauss or Ampere's law. And for volume elements dv, scales from a simple dx dy dz up to the r to the power of 2 sin theta dr d theta and d phi, depending on the systems. Next, we have the gradient denoted as del v. It is applied exclusively to a scalar field and outputs a vector field that points in the direction of the maximum rate of increase of that scalar. The table breaks down the special derivative components across Cartesian, cylindrical, and spherical boundaries. Next is divergence, expressed as del dot A. It operates on a vector field but outputs a pure scalar value. Divergence is highly critical for Maxwell's equations because it measures the net special outflow or inflow, essentially identifying the source or sinks of the field. Moving on to the curl, written as del times A. Unlike the gradient, the curl is applied to a vector field and yields another vector. Physically, it measures the rotational rotation or circulation of a field at a given point, computed using the determinant matrices displayed here. We also have the Laplacian denoted as del square V, which is simply the divergence of a gradient del dot del V. It is applied to a scalar field, gives a scalar result, and physically measures how much a field spreads out or diffuses over a region. To tie all these concepts together, everything we just covered relies on the del operator symbolized by nabla or del. It is a fundamental vector differential operator. Depending on whether we take its direct product, dot product, or cross product. It defines the gradient, divergence, and curl across all the three coordinate systems. Now, let us enter the next core chapter, static electric fields. For this section, we will briefly cover four main areas: the introduction using Coulomb's law, the general concept of the electric field, Gauss' law, and finally electric potential. We begin with Coulomb's law, which defines the electrostatic force between 2 points charged. This force is directional along the line joining them, directly proportional to the product of the charge and inversely proportional to the square of the distance between them, calculated using the standard formulas shown here. Next, the electric field is defined as a special region around a charged object where another test charge experiences an electric force. Depending on the physical arrangement, charge can be distributed across three geometry types: line 1D like a wire, surface 2D like a sheet, or volume 3D like a solid sphere. To calculate fields from continuous distribution, we use specific charge densities as summarized in the table. We integrate the electric field contribution vector E across the respective elements using line charge density ρ L, surface charge density ρ S, or volume charge density ρ V. Moving on to Gauss' law, which states that the total electric flux passing through any closed surface equals the total enclosed net charge. By applying the divergence theorem to convert the surface integral to a volume integral, we arrive at the differential from del dot vector D equals to ρ V, which is Maxwell's first equation. Finally, we have electric potential V, which represents the work done per unit charge against the electric field. The potential at the field point can be calculated for discrete point charge or integrated over continuous line surface and volume charge distributions as detailed in the equations. That concludes my presentations on vector analysis, coordinate system, and static electric fields for Physics 568. Thank you so much for your time and attention.